Okay, so today we're going to be talking about big O notation, which is basically a nice, simple way to understand algorithmic efficiency. So here are some resources that you guys can use later on if you want to learn more. But to start off, what exactly is big O notation? So big O notation is basically the complexity of your function in terms of input size. So generally, big O notation basically will say that a function runs in O of like, and then something, and then n time. So what does that mean? So essentially what big O notation does is it tells you how long your function takes to run and how it scales up, right? So you can have functions that run like at the same speed, regardless of how many inputs or how big of an input you provide, right? You could have functions that run as fast as, or that run slower as the number of inputs scale up. You could have functions that run really fast for small inputs and then run really slow for bigger ones and stuff like that. So that's the sort of thing that big O notation can help us answer. So how fast does this function run? And on occasion, also how much memory it takes up. But that's a different thing for a far different thing. So going back to the big O notation, here's like a series of rankings for them. This goes back to what I was talking about earlier. So the best case scenario is O of 1. So the speed at which it runs doesn't depend on the size of the data set. So one thing to note is the speed will never, or basically never, decrease as the size of the data set goes on. So let me draw a little graph here on the right. Do like let's say this is input size, which is n, and then this is going to be like the complexity, or when we'll call that O. You will basically never have something like this, where let me draw it a little better. You'll never have something like this, where it starts out really slow and gets really fast for big inputs. That's like almost physically impossible. So O of 1, which is the best case, basically just means it's like a flat line. So regardless of if it's like one, like the best way to think about it is like an array, right? If you put in like a small array, it runs just as fast as if you put in a big array. Then you've got things like O of log n, which will basically look something like that. Well, it doesn't asymptote exactly. More like that sort of thing. You'll also have like O of n, which runs sort of like this. You can have n log n, which is more complicated to draw, and I'm not going to do that right now. O of n squared, which is this one, and O of 2 to the n, which O of 2 to the n is really bad. And here's a simple reason why. So just to give you an idea of what all of these all these big O notation functions mean. Let's say that let's say I give you 10 inputs. How long will it take to run the function with 10 inputs? So we start with the first one. For O of 1, it's just going to run at O like the entire time. But for O of log n, that's also going to run at O of 1 in this specific instance, which is good. But an O of n function is going to run at like 10O, basically, which is like 10 times the amount of time that it would take to run on one input. Versus O of n log n, we'll forget about that one. O of n squared takes up 100 times more time to run. And O of 2 to the n is 2 to the 10th power, which is, I think 512 or like 1024, like a really big number of times to run. So the way we determine this O of n efficiency is by just analyzing our functions or by using like a time sort of thing. And we'll run through both ways in a second. So the easy one, O of 1, constant time. So whether you pass in one argument or a million arguments, it's all the same. So good example here is define first element is red. You take in an array, you check if the first element of the array is red. If it's red, you return 2. If it's not, you return false. So why does this run in constant time? Can anybody tell me?
Because you're passing the actual index for the array. It doesn't have to look it up.
Okay, yeah. So we're always referring to one element, and we always know that element's the first element. So we don't have to go through the array at all. We literally just like take it, pluck it out, check if it's true, and we're done. If you get an element with one array, or an array with one element, or an array with 100 elements, we'll see that the time is exactly the same. But let me go ahead and prove this to you. So what I'm going to do is I'm going to pause my screen real quick, and I'm going to copy this over into my VS Code, which is over here. Here, let's change this to that and say else false. And we can just say, yeah. So this is our function, right? It's our define first element is red function. Now, how can I figure out how long it actually takes to run this function? For that, we need to use something called the time library. Now, there's a couple other ones. There's timeit and timer. But for our purposes, we're just going to use the time library. We use your standard time library in Python. Have any of you guys seen or used this library before, or is it relatively new?
New, but are you okay? There we go.
I forget which
Okay.
challenge it was, but we had to use it for that. One of the challenges you guys gave us.
Okay, cool. Yeah, so I think it's been a little while since that challenge. So I'll just run through an overview of what it is again. So the main time has a lot of functions. We can see those by doing time dot, and then you see you can get like the time, you can get get a time tuple, you can get info of the specified clock, you can get the local time, you can get like a process time, not really sure what that is. You can delay execution of some code for a little bit. You get the time in nanoseconds. There's a lot of stuff. But for our purposes, we're just going to use the time.time function. So what we're doing here is, let me go down here. So if I were to print out time.time right now, and let me clear this and let me zoom in a little bit. Oh, that was too big. Yeah, that's good. So what the time.time function does is it basically gets you the time since the epoch, which I believe is defined as like the first day of 1900. I could be wrong about that though, but basically defined as the current time compared with some arbitrary time. And it prints it out in seconds. Here, let's see if it actually tells us. Yeah, returns the current time in seconds, and its epoch fraction of a second may be present if the system clock provides them. And you see here it outputs this long decimal number. But the thing is, this updates every single time that I run this function. So if I run it again, you can see this one is 179 versus the next run at a 196. So you can tell how much time elapses between runs of a function using this time.time function. So what I like to do is we could say something like start time equals time.time. Then what we could do is like run first element is red. And let's come up with let's just do like an array of like one number. Say, and no, turn. And then we can print out time.time minus start time. So what this should do is it'll say, all right, we're starting, I start my timer. I'm going to run everything inside of it and then in the middle, and then I'm going to hit the end and I'm going to print out the difference between when I started and when I ended. So it essentially tells us how long it takes to run a function. So for example, this one basically took no time at all. We can also we can keep extending it. And essentially, this will basically not take any time, regardless of the number of times that we run. So any questions about what the time library does in Python or how we can use it?
No question. This is just a pretty cool way of visualizing it.
Yeah, it's in my personal opinion, it's pretty helpful. Here, let me go back to the slides. All right, so back here. So we talked about constant time. Another one is linear time. So that says here the runtime will grow linearly based on what you pass in. So for example, this one it says, does it contain it? And it goes through an array, it takes an array and a value, and it says for every item in the array, if the item is a value, return true, else return false. So why is this one linear time? Well, while the other one wasn't. So we go back here. This one, again, it doesn't search through the array. It literally takes the array, takes something out of the array, and does stuff with it. That doesn't depend on how long the array is. But this one definitely is going to depend. Oh, I forgot to resume share. Okay. Can you guys see the linear time screen now? Okay. So this one, so again, this example is in linear time. This example is in constant time. The constant time example does not iterate over the array. It doesn't change the number of runs based on how big the array is. But this guy iterates over the array. So if the array is 1 element, you run through this 1 time. If it's 10 elements, you run through it 10 times. If it's 100 elements, you run through it 100 times. So that's basically what linear time means for us. So let me switch back to my VS Code once I can find it. Where are you, VS Code? Okay, there we go. So can you guys see my VS Code now? Okay, cool. Here, let me bring this down a little bit. So again, we're doing exactly the same thing here, right? We're importing time. So we're importing time, we're putting in our function, and then again, we're just doing the start time, we're running our function, and then we're printing out time.time at the end. Let's see. Just trying to think about which other library we could also use. Okay, actually, I think instead of time, let's try using time it instead. That might be better for us. Here, let me just double check that this one works. Ah, perfect. Okay, so the difference between the time and the time it libraries is that time it basically is another default library that's set up to measure the execution time of small code snippets, essentially. Yeah, I'm just trying to think about what the best way is to do this. Yeah, so let's take this, put this in here, and print this. I haven't used this library in a little while compared to the time.time one. I just want to make sure that I'm doing this right. Okay, never mind that. Here, we'll go back to just doing time.time and start time. And okay, let's delete that and do that. So yeah, we can do exactly the same thing. We run it. In this case, again, we get 0.0. Can anybody tell me why I keep getting 0.0 here? Like, that doesn't seem like it makes sense. Because this obviously is taking time to run. So why is it showing me 0.0?
Is
I would
it because it's ignoring all the other decimal places as far as the seconds go?
That could be one.
I was gonna say the input probably needs to be like a lot bigger to make a difference on the road time.
Yeah, exactly. Again, like right now, it doesn't really. It's not taking a very long time to run this, just because I mean, look at how many elements we have. We have 1, 2, 3, 4, 5 elements in this array. It's going to run all of 5 times. That's really like almost no time at all for a computer. But what we can do is we can tell if we wanted to, say, delay the execution of code, we can delay it for like 1 second, for example, which is a decent bit of time. And we can see that down here. If we look at the difference between the start time and this next time that we have, after I incorporate this 1 second delay, right, we have the start time is, what is it, 659.017. And then the end time is like 660.019. So the time.time works. The only reason we don't see it working is because there's basically no difference for small sample sizes like this one that have like five test cases, or an array with like a size of 5. Now, you can make random arrays that are, instead of 5, let's say like 500 or 5,000 elements long. There's code to do that. Then you can run the time.time start and end on it. But in our case, we generally don't really need to use those, especially not for toy examples like this one. But again, there are libraries that can do it. I think some of those should be linked in the slide deck. But if not, and if you're interested, feel free to let me know and I can send them to you as well. So, okay, I think we're pretty much done with the VS Code for now. And again, for linear time, right, we have, again, like our O and our N, O up here. It just basically, again, grows like linearly, like a line. Next up is going to be quadratic time, so which is a decent bit worse, right? So for quadratic time, this one will, we have our N, we have our O. This one will kind of do something like that. That wasn't great. Let's try that again. Yeah, something roughly like that. Where again, it's basically squaring, right? So if you run, so let's look at this function with all combinations. If I run this with an array size of 1, everything runs once. If I run this with an array size of 2, well, the first for loop has to iterate twice, and the second for loop also has to iterate twice. And 2 times 2 is 4. If I run it with an array that has 3 things in it, the first for loop has to run 3 times, but every time the first for loop runs, the second for loop also has to run, right? So this one's going to run 3 times. This one's also going to run 3 times. And then that's going to be 3 times 3, which is 9. And so on. So this one, as you can see, scales up a lot faster than the linear example that we saw on the previous slide. So again, based on your input, the amount of time that it takes to run will, basically it'll square based off the size of the input. So there's a few takeaways from this. So we'll talk about hashes later on, so don't worry too much about the first point. The second one, avoid nested loops, because look back here again, the more nested loops you have, the more complicated your code gets, and the more time you end up running over an iterator. The more times you iterate, the more complex it gets and the more bogged down the code gets. Also, lastly, if you find yourself writing code that has poor big O complexity, so say like a lot of nested loops, there's probably somewhere you can refactor. So that's generally something good to keep in mind too. Also, recursion is another case where big O efficiency is sometimes, or it's sometimes recursion can be big O efficient, and sometimes it's really not. So you'll want to go case by case for recursion and determine, hey, is recursion actually speeding up my code here, or does it just make it look nice? Because that's often a trade-off that you'll see. I think that's all in the slide deck. Do you guys have any questions about that for now? Okay, cool. So let me go back to VS Code real quick. And we don't need this anymore. Don't need this either. What I did want to talk about was logarithmic time as well, because that one is a little bit strange. So generally, if you don't have a recursive program, those are generally going to be like O of n or O of n squared or O of n cubed or like something nice and simple like that. Generally, if you have a logarithmic time complexity, that'll often be recursive. And it's when the time, I think the README for today talks about this more, but it's when the time basically gets like divided. Or the problem gets divided into pieces, and every time like a new piece of the problem gets taken. Then there's also n log n, which is something that you use a lot for searching and sorting, in order to basically just actually actually searching and sorting. It basically just splits everything up, and then at the end it also puts them back together. So that creates an n log n type of structure. Yeah, I think that's honestly about it for big O notation. Do you guys have any questions about it? I know this was a very quick lecture, so. Okay. Oh, go for it.
Do you know any good examples of what would be like a good recursive versus a bad recursive? Like if you're thinking about it. Like I'm guessing if you have a lot of like for loops in the original problem and you're kind of trying to do that recursively, that'd probably be like bad. But if you have like just a while loop somewhere, I mean, I don't know, but I don't know if that's a good question or not.
No, that is a good question. Fibonacci numbers is probably a good example of recursion, because from what I remember, it's equally complex. But bad examples, maybe something like flipping around a string. That might not be. Actually, no, that would probably be equally bad as just doing it regularly. Yeah, I don't think any examples come to mind, but let me see if I can find some. 'Cause that's a good question. Uh, oh, and actually, Philip, yes, you are correct. Fibonacci is a lot more work than recursive. So thank you for that correction. Here, I'll post if anybody's interested in going in a little bit more detail. There's a good document from a Stanford CS course that I've definitely used before that I can recommend. I popped it in the chat. It's pretty short, but hopefully it'll help. But basically on page 3, they have a diagram of the Fibonacci problem. And for n equals 5, and you're basically like creating a bunch of, I don't know if you guys remember the stuff about binary trees, but you're basically creating like a bunch of trees and then running it through those. And obviously that creates a lot of sub processes, which isn't necessarily the best or most efficient approach. But yeah, also in general, like recursive algorithm time complexity is a little bit more complicated than just the time complexity of things with for and while loops, just because of the like calling each other and calling them back. So there isn't as much about it that's like lower level, but if you want to delve into like the math of actually calculating how like using formulas to figure out the efficiency, there's a lot more material about that. Other questions? Okay, so I'm going to go ahead and